Okay, welcome back to EME 3214 Mechatronics at Lawrence Tech here, Professor Jim Kearns. I'm going to create a whole series of these, hopefully short. I try to keep them short, but sometimes you get into the subject and just have to get into it, a series of short videos where we cover specific topics. This first one will be transfer functions. We'll look at time response. We'll look at the frequency response and some Fourier stuff, and system identification. I've got some videos on Laplace transforms and Bode plots. I'll probably leave those. I might come back to those. But what I'm going to do is I'm going to, rather than give you a big lecture and all the theory, I want to keep these practical. I want to keep these basically. I'm going to do some examples. I'll work through an example, and I would encourage you to get the pencil and paper out and work along with it. If I make a giant leap in algebra or a giant leap in a transformation from the differential equation to the Laplace domain equation, stop the video, work out the intermediate steps, make sure that you get to the same answer I got to, and if you don't, one of us made a mistake, and if I made the mistake, point it out and we'll fix it. But make sure you can do what I'm doing so that you get this on an exam, and we'll just chunk into this, and I'll create the extra videos as we go. There's nothing polished here. There's no big PowerPoints. I've got exactly one page of notes on this whole thing, so it won't take us that long, I hope. And I will also I'll use MATLAB towards the end to do some simulations and show how this works. You can build the models in MATLAB if you want. Some of the other videos I would encourage you to have MATLAB open as well, because we'll be going back and forth more than on this particular one. So there is our spring mass damper. This box here is our mass. Sits on some wheels. It has a mass of 5 kilograms. Believe it or not, this is supposed to be a spring. Okay? I think I've already given you my this is why I'm an engineer, not an artist joke, haven't I? Okay. But the spring has a constant of K of 3, so the spring force will be, basically the force will be 3 times the delta x, the difference in position from wherever the unsprung position is, or the natural position. This is a damper with a damping coefficient of 2. The force on a damper is, of course, B times x dot. And I'm leaving this open to having some initial conditions, like having a initial position 0.5 meters away from where it would normally come to rest. And we're also going to be applying an external force of some form or another, step function, sine functions, whatever. We'll be applying those as we go and illustrate how they work. And we'll talk about the forced response, the free response, and we'll play with some of these constants in MATLAB to show you how the equations change and how how the actual response happens in, well, it's not real life, but a simulation of real life. Okay, so let's start out with what we call Newton's law, right? F equals ma. That's always a good place to start. Or actually, I should say the sum of the forces, because that's a bad sum I drew there, right? Sum of the forces equals mass times acceleration. We know the mass. We are going to calculate or input the forces, because there's going to be the external force, force to the spring, force to the damper, and then we can calculate acceleration, and from acceleration we can calculate things like velocity and position just by integrating. So let's write out our equation here. We can say that mx double dot, that's our ma, equals the sum of our forces. We have some applied force as a function of time. We have a, these are minus, I'm sorry. We have our force due to the damping, which is Bx dot, and we have our force from the spring, which is, I'll just Kx, okay? So there is an ordinary differential equation. Trying to solve it as a differential equation is difficult, but we can slide this into the Laplace domain quite nicely. Let me just, there we go, give me some more room to work. And I can do this pretty much by inspection. I'm going to rearrange the equation, put the force on the right by itself, put all these terms which are a function of x on the left side of the equation, and I'm going to transform the whole thing into Laplace domain all in one big step, because it saves time and I have it written down. And if you need to do those steps, if you're not comfortable, take the time, pencil and paper, work it out. Pretty much this whole exercise can be done on pencil and paper. So, starting with the force on the right side of the equation, I don't know what that force as a function of time is at the moment, so I'm just going to write it as F of S. And that's equal to, we have the transform the force K here. So it just, since it's just X, it's just K X of S. Let me write that better. K X of S. And our convention normally would be, these would be uppercase and these would have been lowercase in the time domain, but it's just too hard to write it that way, so use your imagination. I'll transform this term next. Oops. Went crazy with the eraser. Oh boy. Okay, so my B of x dot is B times S times x of S. And, multiplying by S is the same as the derivative. And I also have an initial condition that I need to account for, and that's just x at time equals 0. That's the time-based value of x at time equals 0 is our initial condition. The erase is too fat. The next term is that's a plus, is the mass times acceleration term, and that one I'm going to need a little bit of room, so that's ms squared, because it's the second derivative, x of s, minus the initial condition here for x dot, since I'm making a derivative from x dot 0 minus, and I'm taking the derivative of the initial condition of x, so it'll be s x 0, and there's a plus sign there. So there is our transformation and rearrangement from Laplace domain to, from a time domain differential equation to our Laplace domain equation, okay? And I'm going to rearrange it yet again. And what I'm going to do is factor out x of s all by itself. And I will come up with, or I'm going to solve for x of s, I should say, not factor it out. X of s equals 1 over ms squared plus b, let's be consistent here, make that lowercase, bs plus k plus, times f of s plus x dot of 0 plus 1 plus s x of 0 all over ms squared plus BS plus K. Okay? Again, if you need to stop this to go through the algebra, feel free. But basically, I've solved for x of s algebraically, which is a lot easier than solving a differential equation. I have this bit of equation which represents how this system is going to behave as a function of our external applied force. This part of the equation goes to the particular solution, and here we have the response of the system due to these initial conditions, x dot 0 and x 0. And so this is the homogeneous portion of it, and I can divide these up into two actual separate equations and solve them independently and simulate them independently. And then because this is a linear system, I can then come back and put them both back together to get the response to a forcing function and to the initial conditions all in one big thing. So this particular solution tells us the forced response and this tells us the free. Okay? And then what I would do, like I said, I can, well, I'll rewrite them. So I'll say x of s forced equals 1 over ms squared plus bs plus k times f of s, x of s free equals x0 plus 1 plus s x0 dot, x0 all over the same denominator. We have the same denominator in both cases, and this denominator is called the characteristic equation, ms squared plus bs plus k. And those are good things to remember for an exam. You know, the particular solution or the forced response comes from this part. The homogeneous free response comes from that part, and the denominator is called the particular solution. And when we look at the roots of that denominator, they will tell us a lot about how the system behaves. Okay, so those are my two things. At this point, I'm going to jump into MATLAB. MATLAB. And I have a model here. And let me get all of the pieces I need. Okay, so this model, I didn't put the transfer functions in this model. I took the differential equations. This is my sum of forces right there. I divide by the mass. That gives me the acceleration. So I've just taken the differential equation, rearranged it a little bit, integrate that. I get velocity. I multiply velocity by the damping force. That gives me one of the forces I needed back here. I take the velocity, integrate that to get position. I can multiply the position by the spring force. That gives me the third force here that I needed back in here. And then I have an external force, okay? And I have a scope here that tells me the acceleration, the velocity, and position, and another scope that gives me the forces. So I've got inputs, outputs, the internal things. If I run this, dink. Okay, so if I run this, I can hit my square here to get these to pop up, and I'll hit my square here to get these to pop up nicely. Okay, so we have the response here pasted into my journal so we can draw on it. Unfortunately, those lines are kind of skinny, but let's talk about the external force here remains 0 the whole time. The spring force has an initial value here of 1.5 because we have this initial displacement. The position here is at 0.5. So there is an initial force here. Since the initial velocity is 0, my initial damping force is 0. Okay? Velocity starts out at 0. So I have a force, I have that results in an acceleration, and of course, as it accelerates and moves, my spring force decreases, and eventually it does a little oscillation, and eventually in my position here, we will get to zero, the equilibrium position, spring forces go to zero, and everything else goes to zero as it grinds its way to a stop. So that is the free response, the response due to the initial conditions. Now, if I go back to MATLAB and I set my initial condition here to 0, okay, and I have my external force, I'm going to make it go to 3 to get a little nicer response instead of just 1. Okay, I can run that simulation, and so now I have the response due to that step function. That happened at 1 second. It went from 0 to 3. Up to that point, you can see there was no stamping force, there was no spring force, the position was at 0, the velocity was at 0, and the acceleration was at 0. But the instant I apply this force, my acceleration happens, okay? And the velocity starts to pick up. That as the velocity picks up, I start to get a damping force, and I also get to, as it starts to move, I get a spring force. Those forces reduce the acceleration as soon as it starts moving and as soon as it moves some position. So it basically, I pushed it, it kind of bounced, I pushed it. Let's look at position. We started at 0, we went over 1.5, overshot a bit, came back and oscillated. And eventually with this force applied, where our steady state position is going to be, it's going to settle out here at 1 with a force of 3, which if we go back to our spring constant here, we said that our spring constant was 3 times delta x. So our steady state is, for our unit input, if I put 1 in instead of 3, we would have gotten a final resting position of 1/3. And that's, again, our steady state gain here that we could calculate from that case. So that all makes sense. And that was so here we have the homogeneous response or free response due to the initial conditions. Here we had 0 initial conditions, and we applied a force. And if I go back into MATLAB, I can make that back to 0.5. Okay, and then I run my simulation. And here we have, click there, the combined response to the initial conditions and to the applied force at 1. So that's how we play with these systems. Now let's take one little bit of, go back to our pencil and paper now that you've seen how the system behaves. Okay, so I have x of s, and I'm going to make x of s over f of s, make it a transfer function form, equals 1 over ms squared plus bs plus k. Okay, that's our response to a force. And we could play with either equation, the homogeneous or the particular. We typically, for system ID and for a lot of things, will want to express our equation in this form: omega n squared all over s squared plus 2 zeta omega n plus omega n squared, okay, is a standard form. And particularly when we do system ID, we can identify things like omega n and zeta. Or if we want to just understand how the system behaves by putting it in this form, omega n gives us our frequency, our natural frequency, not the damped natural frequency, but we can calculate that. It gives us our natural frequency, and it gives us our damping, and we can tell a lot about how the system is going to behave just from those numbers. So if I look at these two equations, I find that omega n is equal to the, well, I have to do k over m, e over m, erase the m there, okay. Omega n is equal to the square root of k over m, right? Zeta equal, that's a bad zeta. Someday I gotta learn how to draw those. Equals b over m times 1 over 2 omega n, okay? So now I have all the numbers that I need to do that, and so that's just equal. Now here I had a 1 in the numerator, and here I have an omega n squared. So to make that work out, omega n squared is k over m. So when I divided, I divided through by m. Sorry, I missed a step here. 1 over m when I divide through by m. So I need to put a k up there to get omega n squared, because omega n squared equals k over m. I already got 1 over m. So to make this equal to 1 over m, I need to have a multiply by k. I'll just do it this way. So I'll put k over m, and I'll put a 1 over k out here for my static gain, and then of course k over m is omega n squared. So this is my equation in the standard form like that. I can see that my steady state gain is going to be 1 over k. That's essentially what we gave it here. And I think I'll knock this one off right here, because we'll talk about frequency response separately. So I can take the same model, apply a sine wave, and see how it behaves as a function of different frequencies. I can see how changing the damping and things will affect that. So I think at this point, we're going to stop this lecture to keep them reasonably short.